There was a presentation that was missing. I think somebody pointed out last time. The link state, I put it up. It was a bit hard to find because I thought it looked like it was there, but then it was not there, which is the link state one, not the distance vector one, which is what somebody told me, because it is there. So that should be all up. That was it, right? Yeah.
And also, Ian, I think, uploaded a second exercise.
Yeah.
But not with the diagrams.
Yeah, so he's put 2 on there. So so the diagrams, yeah, I know what you're saying, but he'll put 2 more. So I think if you do the ones he's given, you should be pretty set for the prac. So there'll be 2 more that he'll put up as well. But let me know how that goes. See, I'm wrong. The lecture's already started, guys. So this is just me being nice, because I felt nice. If you're late, then you miss out. But it's already up. So where we stopped off talking last time was about the link layer. And what we wanted to focus on was the link layer is about error detection and error correction. So hopefully by now you've seen an example of how to do internet checksum, right? Hands up, yeah. It's 1's complement, yes. How to do 1's complement, not 2's complement. You don't discard the carry, you add the carry back. And how to check if there's an error, add it all up, take the 1's complement, you should get a 0, right? If there isn't one. So the thing I want to continue on today was just to go over the idea. You send something, you add some extra information. That extra information is in turn going to help the receiver determine if there was an error in the bits that were sent, right? Okay. So remember, our focus here is a link, right? From one node to another node. So today, in addition to checksum, I wanted to talk about. Do you guys have any questions on that? If not, we can start talking about parity bits, right? So which is this idea is really old. It's simple. You still find, if you guys ever used a terminal or set up a COM port, communication port, or RS-232 port, you would find that you have to define whether to enable parity or not, right? So parity checks are still used. But what you'll see is that, for determining errors in today's traffic, right, in long bit streams, parity is not powerful enough, right? But however, it is still used. So, and it is a nice simple concept. So you can talk about odd parity and even parity, essentially. And the idea with odd parity is, so if this is your data bits that you want to send, right, what you do is you add a parity check bit, right? If it's odd, the idea is that when you count up all the number of ones in here, with the parity bit, it should be an odd number. So in this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's already an odd number. So your parity check bit's going to be a 0, right? Okay. But if it's even parity, the idea is that if you add up all the ones, so here I think it's the same one, so which means we have 9 ones. So to make it even parity, we add a 1 in here, right? So that's the idea. Okay. So so this would be what the sender does. Then at the receiver would just add up all the ones here and see if it's an odd number. And in this case, the receiver would add up all the ones here and check if it's an even number of ones, right? So in terms of error detection capability, so how many errors can it detect? So hopefully it's easy to see that if I was to flip, maybe this one to a 0, right? And then at the sender, what would happen is when you count the ones, you'd end up with 8, right? Because I just changed that 1 to a 0. Yeah. So that means because it's odd parity, it would come up as an error, right? Yeah. You all with me? So the good news is that you can detect at least a single bit error, right? So we can detect single bit errors. If you're not convinced, so let's in this case take a 1, right? And what happens if this bit gets flipped during transmission? So if you count the ones here, now you'll end up with 9, right? Yeah. So that means it's an error, because what you have is an odd number of ones, right? Okay. So convince yourself that you can detect a single bit error, right? What's a failure case? Should be. What's a failure case for parity, single bit parity? Yeah, exactly. So things aren't so pretty if this one and let's say both of these go to 0. Right, 0. So now we have 1, 2, 3, 4, 5, 6, 7, 8, right? So the receiver goes, oh, even parity, even number of ones, no error, right? So basically, there's no guarantee of picking more than 1 bit errors, right? However, it can do better, right? It can do better because what if I flip 1 more bit? Let's take, this 0. And then turn that to 1, right? So now I end up with an even bit, right? So so as long as you have an odd number of bit flips, right? If you have odd number of errors, you can detect it, but if not, you can't, right? Okay. So we can do better. Right. So that is so whether it's even, whether it's odd or even parity, if you have odd number of bit flips, then you should be able to detect it. But if it's even, then you can't. Okay. But you're guaranteed. What you're guaranteed is this, right? This is your guarantee from parity, a single bit flip error, right? But you can do better sometimes. But so do you think when you have noise in channels, you get only odd number of bit flips? Noise is going to go, I will flip exactly 3 or 9, or, you know, it's never going to happen, right? Okay, noise is not going to cause an odd number of bit flips all the time, right? So it's useful, but it's not so useful, right? Because unfortunately, noise doesn't cause odd number of errors all the time, right? Okay. Do you have any questions? Is that clear? The example's okay? Yeah? Right, cool. So the part I want to talk about here is, so it cannot, typically what happens is that in internet traffic, what you get is what's called burst errors, right? So burst errors are when you have some substring of and these or bits are flipped, right? Let's say. So what happens in reality is you don't just get odd number of errors or even number of errors or single bit errors, right? So you don't always get odd number of errors, single bit errors, or even number of errors. What you get is a whole bunch of arbitrary length bits just being noisy, right? Being flipped. Why is that? Because typically if you think of traffic is bursty, noise is similar, so you might have a large amount of noise at one time in a wireless channel because everybody's using it. So all those bits sent in that moment, right, might be damaged, right, or flipped, okay? Or maybe so noisy that the receiver can't detect whether it's a 1 or a 0, okay? So that's what typically happens. So unfortunately, errors don't occur in single bits, or odd number of bits or even number of bits. What you typically get is a whole bunch of bits that are in error, right? Okay, or gets flipped. So parity doesn't work so well. But you know, we can do a little better with parity. It's not so bad, because to kind of address this problem, people came up with 2D parities, right? So there's this examples in the thing that I just gave you. So 2D parity, the idea is that instead of protecting, let's say, a single byte, right, using a single parity bit, we're going to use a two-dimensional parity vector, right? So that is, we have, so this is a column. So you have a column parity, and then you also have a, oh, what am I saying? Sorry. So this is row. And then you have so in this example, 1, 2, 3, 4. So this is even parity, right? So this is your data, and this is the extra information that you're sending about your data to help detect or correct errors. So in this row, if you look at it, you got 1, 2, 3, 4, 1, 2, 3, 4. So the parity bit is 0, etc. And then that's your row parity bit. You also have a column parity bit. If you go 1, 2, 3, 4, even number of ones, 1, 2, 3, 4, right? Even parity, etc. If you go the last one, 1, 2, 3, and 4. Okay, so these are your parity check bits, right? And this is the data that you want to send. Yeah. Right. So they're protected by. So this is the extra information you have to send. That's your overhead, right? The price to pay. No free lunch part. Okay. So the nice thing now is, before with parity, you could only detect. So if you go back to this example, the simple example, we had a single bit that was received in error. We knew something was wrong, but there's no way to tell exactly which bit was in error, right? We don't know. Yeah, you can't locate the bit that's in error. You just know something was wrong, right? How do you know it's this one or this one or that one, right? But the nice thing about 2D parity is that we can actually locate the error, right? So here's a, so it's guaranteed to at least detect and correct single bit errors, right? Correct at least single bit errors. So this is the guarantee that it provides. Okay, as long as only one bit has flipped, you're guaranteed to be able to detect and correct it, right? But it can do better. It can do a little better. So in this example, we'll see that this bit here, 1, 2 down, 1, 2. This one is, right, this one's flipped, yeah? So let's see how that works. Essentially, this will check, right? So the receiver will go, oh yeah, 1, good, yep, good. The receiver goes, checks the next byte. Is it a byte? 1, 2, 3, 4, 5, 6, 7. So 7 data bits and 1 parity bit, so it's a byte. There goes 1, 2, 3, 4, 5. So because this is even parity, you know there's an error here, right? In this row, but we don't know where. Okay, so all this will check out okay. If you go the same way, this column checks out okay. This column should check out. But if you go along here, you'll see 1, 2, 3. So you know there's something wrong along this column and this row, right? So this is the this is the location of the bit error, right? So in this case, you don't need to ask for a retransmission. You could potentially correct this bit, and then you're done, right? Yeah. So what's the nice thing about being able to not only detect but correct errors, right? You don't need a retransmission. Fix it up yourself. So like I said, we can do better sometimes. So here's a situation that we can correct. So we have, if you go back to the previous one, so we can see that this one has changed, right? And 1, 2, 3, 4, 1, 2, 3, 4, right? This one has changed, right? Okay. So in this case, it turns out that we can detect and correct it, because this will turn out to be wrong. This parity check will turn out to be wrong. So you can locate that bit. And this will turn out to be wrong. And this will turn out to be wrong, right? So it turns out you can do better sometimes, as long as, what? As long as, yeah, same row or same column, right? So as long as there's somehow the errors occur in different rows or columns, you're able to actually do better, go better than you guarantee, right? So detect any number of errors in a single row or column, so odd and even numbers. So as long as these errors are occurring in different rows and columns, you're okay, right? Yeah. Because if this error happened here, right, if it were to happen here, then what would happen? So you have 2-bit flips, right? Can you detect it? Will this, if this was a 1, what would happen to this parity check? Would it fail or pass? It would pass, right? So you can't detect it anymore, right? You can't correct it anymore. Right? Okay, the columns will fail, but you don't know how, but you won't be able to correct it anymore, right? So as long as the errors are not on the same row or column, you can correct it, right? So notice the distinction between being able to correct versus being able to detect, right? Just because you detect doesn't mean you can correct it, right? Yeah. So detection. Detect any number of errors in a single row or column, odd and even numbers. So here's an example where we have 2 errors in the same column. What you'll see is that obviously this column should be okay. So you have 1, 2, 3, 4, passes a parity check, even parity check. But if you go along here, you've got 1, 2, 3. So you know there's something wrong in this column. You go 1, 2, 3, you know something's wrong with this column, right? So you're able to detect, right, errors, but you can't correct them. Yeah? You're able to detect. Keyword is detect, but you cannot correct them, right? So any number of errors in a single row or column you can correct. So compare that to wrong one. Sorry. Compare that to our. So it's better than using single bit parity, because with single bit parity you had to have odd number of flips, right? Sorry, even number of errors. No, I take all that back. If you have odd number, you can detect it, right? But in this case, with 2D parity, you're doing a lot better, because any number of errors in a single column or row you can always detect, right? Which is pretty cool. Couldn't do that before with single bit parity, but with 2D parity, any number of errors. So we're getting close to being able to detect burst errors, right? Which is a whole bunch of bits going wrong in a single string, right? Okay? You can't correct it, but doesn't matter. You can always have a retransmission, right? Things go wrong, okay? So the guarantee is the detect and correction of a single bit error. You can do better sometimes. As long as those errors are occurring in different columns and rows, that means you can detect and correct them, right? in terms of detection, as long as all the errors are occurring in a single row or a single column, turns out you can pick them up, right? So it's not bad, pretty powerful, right? So no, it doesn't protect against everything, because show you a simple counterexample. So look what happens with this example, right? So we have 4 bits, 1, 2, 3, 4. Notice they're now occurring in obviously different rows, right? So not a single row anymore, and not a single column anymore, right? Okay. Look what happens to a parity check. So you go 1, 2, 3, 4, done. You go 1, 2, 3, 4, passes. 1, 2, passes. 1, 2, 3, 4, passes. Right. So 2D parity fails, right? So when you have errors in more than one row or column, you can't even detect them, right? So it's closer to what we want, but not quite, right? It's not good at doing burst errors, right? Burst errors are not going to happen in a single row or a single column. There's going to be there might be a whole bunch of bits that are in error, like this, right? That's what reality is like, okay? So we need to be able to detect errors in multiple rows and columns, right? What we want to be able to do is this. We want to be able to, we need something more powerful. So that's what the next thing we're going to look at is, right? Called cyclic redundancy checks, okay? Do you have any questions with the 2D parity stuff? No? All right. Okay, so let's do a quick example. You can do a quick example. So if you go to my uni, didn't have time to write up. There should be a look at the first question I posted on today's slides. Let me put it up in a sec. Wow, you're so slow. My uni's so slow. Oh no, Echo 360. Should be the first question on today's lecture. Slides. So this is on a 2D parity example, right? See if you can do it. So that's a stream of bits you send. Clearly, you can't send a two-dimensional vector through a wire. You have to serialize it, right? Yeah? So this is a serialized version of a 2D of a data packet protected by 2D parity, right? So your first job is to figure out the size. So remember, although it's nice to write like a box, but in reality you can't send a box, right? So you got to send it as a bit stream, right? So for you to be able to find the error, you'd need to turn it into a box because it's easy to do the calculation, right? So what's your n by n matrix? N by m or n by n matrix? I think there's only one possible. Take a piece of paper, write it out. Split it up into a matrix, 2D matrix. Otherwise, well, you might be really smart. You could do it in your head. I have great admiration for your skills. I did put it up. So write it out as a 2D matrix. Can you do that first? Have you got it written down as a 2D matrix? You need to know the dimension of the matrix. What would it be like?
Are the rows and columns always the same number?
Do the rows and columns have to be the same number? Uh-huh. What way can you split it? Yeah. Yes. N by n. I think there's only one way to kind of split it. Is there another way to do it? 5 rows of 3. Is that 16 bits? God, I hope I didn't make a mistake. Can you guys count 16? Oh, okay, that's good. How can you make 16? 5 by 4, 2 by 6, 8 by 2. Is that going to work? 8 by 2. Is 8 by 2 going to work? No, it's not going to work. 6 by 2, 12. There's only one number that works. It has to be what? Shout it out, someone. 2D matrix of what? 4 by 4. Okay, good. 4 by 4. Write it out. 4 by 4. Come on. You got it? Yeah. Okay, 9 submissions. Come on. Huh?
Does the bit stream include the
Parity bits.
parity bit?
Yeah.
So that means there's only 3 by 3 of data, but it's 4 by 4.
Uh-huh. It's like this. Yeah, so it's like that, like this one here. So the data is 7, right? This part. This is the parity. So now that you started thinking about it, you'd send this, right?
Yeah.
Because you have to serialize it. Yeah?
So that would be 64-bit stream.
In this case, 8 times, yeah. So you got it? So I know there's at least 30 people in the class. Let's say 50% has devices, so 12. 3 more. 243. Does that mean that many people are watching? No, can't be. Doubt it. It's winter. Winter? Autumn? I don't know. Yeah. Okay. I think I can't remember which one's the right answer. Anyway, we'll work it out. 14. One more. One more. Brave soldier. Come on. Yeah, okay. Let's see what you guys think. Yay, pretty good. All right. So most people thought it was B, I think, from memory. B is the right answer. So how do we get that? Let's pick the empty sheet from here. So clearly, if you look at this bit stream, there's 16 bits. There's only one sensible way to divide this, which is into a 4 by 4 matrix, right? So if I break it up into 4 by 4 matrix, I think I end up with 0, 0, 1, 1. I am going to get this wrong. Can somebody shout it out? What's the next row? 1, 1, or 1? 1, 0, 0, 1, right? Okay, so that's 4 by 4. I better switch because I think it only records one screen. Okay, so that's, and essentially the question you had was which part is the data. So this part is the data, right? And I think I said even parity, so that means if you check here, that one is okay. 1, 2, 3, something is wrong. 2, even parity is okay. If you go here, 2, that's okay. Something is wrong. Here is okay, right? So that means my error must be here or here. So it's this one over there, right? Okay. So the correct answer is one with that set to 0, right? So single bit flip, and we're able to detect and correct it, right? Is it good? Which one? This one? Yeah, it checks out okay. 1, 2, 3, 4, and 4.
So it's for both of them?
Yeah, should work out okay every time. Are you guys good with that? Can't send a 2D matrix, have to send a stream of bits, right? But that's the way the calculation is done, right? Okay. Questions? Okay, cool. All right, let's get our hands dirty with CRC. So there's a whole bunch of notes, but you know, I don't want to go too crazy, but maybe a little crazy. No, maybe not. May not need it. So with the problem with parity and 2D parity is that they're not very good at detecting burst errors. Burst errors are arbitrary bit lengths, right? All consecutive, right, bits just being in error because they don't just happen to nicely fit a single column or a single row, right? So something that's way more powerful is cyclic redundancy checks, and this is pretty much used everywhere on the link layer, on so many protocols, right? Because it's simple to implement in hardware. Because it turns out to do CRC checks, all you need is a single gate, XOR gate, right? XOR operation, right? And it turns out you don't even need an adder, right? Because you ignore the carry bits. You don't need to worry about carry. It's just XOR operations, right? So you can implement it in hardware and do it really, really fast. Okay, so that means if you have a high data rate link and then you want to be able to do error direction correction, CRC is a good way to go, right? Because you can do it really quickly in hardware, right? With just implemented using XOR gates, right? So that's why CRC is very popular. And the other thing is you can kind of tailor your error detection capability, right? That is, if you want to detect large burst length errors, you can use a different CRC generator polynomial. So if you have a good understanding of the erroneousness of your link, then you can go and find a decent CRC generator polynomial to create enough redundant information for the data you want to send to be able to correct those burst length errors, right? So which is beautiful, okay? Because as a network engineer, or someone who's designing a protocol, or someone implementing, it gives you a good choice, right? In terms of how you want to do it, and the price you want to pay in terms of the extra information you want to send, yeah? Right, so which is really cool. So the general idea is essentially with CRC is to find, for some data D, right? This is the stuff you want to send, right? If your payload, okay? Is to be able to find some extra redundant bits, right? Such that if I was to divide D and R together with what's called a generator polynomial, right, which is called G, right, which is here, okay, you get back 0, right? That means I want to find R such that if I put it together with D, right, it divides without a remainder by using another number called G, right? Okay, so the goal is to find what is that number that I can put in here such that if I was to take this whole piece of data and divide it by G, I get a remainder of 0, right? That's ideally what I want, right? So this is the data you want to send. My goal is to find the extra bits such that if I divide this whole thing by g, I get a 0 as a remainder. Okay, right? If you think of the data as 8 and my generator as 5, my goal would be to add 2 to 8, which gives me 10, which is divisible by 5 with a remainder 0, right? Simple example, okay? But we do this in binary, right? Because we do it in binary, we use, and all binary strings, turns out, can be represented as a polynomial, right? Polynomial just means, x squared, x plus x cubed, plus 1, whatever, right? Any of these equations that you come across, okay? So without going too much into details, I would say the way to think about it is just simply what I just said. Essentially, we have data that we want to send. We want to find an R, right, such that when we divide it by some number g, we get back a 0, right? Okay? How do we do that, right? So to be able to do that, the first thing we need to do is remember that all operations are, in this, for CRC checks, is an exclusive OR, so we don't worry about carry. So that means addition and subtraction is the same operation. There's no difference, right? Because there's no carry. Okay, everything is an XOR operation. Okay, and the other thing is that in terms of what we need to do first is, so the first thing we need to do, if you like, is to take our d, and so multiplying by anything 2 is the same as what? How do you multiply in binary? Binary by 2 to the power anything. What do you do to the bit stream? Do you shift left or right? It's a shift operation, right? You guys did computer systems. I can see some faces from computer systems, right? So multiplication is a bit shift, right? So first we multiply by 2 to the power r. Now r has some significance here, right? Because r essentially denotes the extra information bits that you want to add, okay? This r actually defines the burst length error you can detect, right? So if I have a CRC code that has r redundant bits, that means I can correct burst errors of up to r bits, right? Okay, that's what that means, okay? So what we're going to do is, first what we do is we create space for r bits, right? And then we add the r, such that it should be divisible by some factor. It should be a factor of what we call g, right? So n times g, right? It should be a factor of g. So how do we go about finding it? So we can subtract r from both sides. Remember, addition and subtraction are the same. So essentially, I XOR r on both sides. So I bring r to this side, right? And then I can, to get r, all I have to do is divide both sides by ng, right? So that's what I do, right? So what I have left is then my remainder, right? Okay, so it's very simple to work out the formula for how to get r, right? You bit shift by r bits because we're going to have r, we want to correct burst lengths of r bits. And that result should be divisible by some factor of g, which we haven't talked about yet. And then to find what r is, all we have to do is take 2d shifted by r divided by g. Okay, so that's essentially your CRC calculation operation, right? So how do we get a good g, right? So how do we get a good generator polynomial, right? So this guy here, how do we get a good generator polynomial? So everything, the power of CRC is totally dependent on choosing a good generator polynomial, right? Luckily for you, or for me, we don't have to do that because there's a whole bunch of good stuff out there. The key property of this generator polynomial is that it should be a primitive, right? Primitive polynomial. Primitive is like same as prime, right? Okay, that means the largest factor should be the degree of polynomial less than 1, right? So that means there's no other number that you can divide this polynomial by, right? Other than, let's say, 1 degree less than itself, right? So you don't have to think too much, but there's a whole lot of good primitive polynomials out there, and then it's very easy to look this up. because this is just a wiki site that I just pulled up on CRC. It even has an example of a CRC calculation. So if you don't follow mine, you can go up and look it up as well. So if you go down to the wiki page on CRCs, you'll find that there's a whole bunch of really cool CRC polynomials. So the CRC1, clearly it's not very good because it has, this one has degree 1. So this is x to the power 0, x to the power 1. So it can only correct burst errors of up to 1 bit, right? So R is 1, okay? So this one has degree 3, so it can correct burst errors of up to 3 bits, right? How do I get this number? Because every binary number, so this is 2 to the power 0, if you like, coefficient. This is 2 to the power 1. This is 2 to the power 3 coefficient, right? So you can write any binary number as polynomial. So if you want to correct, burst errors up to 32 bits, so there's a CRC even 64 here, which is an ISO standard, right? So if you guys are doing this stuff, you don't want to come up with your own generator polynomial. Go look up a standard one, right, and use it, okay? Because that is already primitive, and it guarantees the error correcting bound, which is being able to correct burst length of R bits, right? Okay. But if you come up with your own, chances are it may not be able to give you that guarantee, right? So if you use the CRC64 ISO polynomial, which is, so this is a 1, and then 0, 1, 1, 0, 1, 1, lots of zeros, and then 1, right? So if you use this one, then essentially you can correct up to burst errors of 64 bits, right? That's pretty good, right? It's pretty decent, 64 bits going wrong in a bit stream, you can correct it, right? But the price to pay is how many redundant bits do you need to put for this CRC64? How many redundant bits? Huh? How many? So it's degree 64. How many redundant bits? 64, right? Okay, so you got to pad 64 bits. That's the price to pay. But you get this cool property. 64 bits going wrong consecutively, I can detect it, right? So there's a price to pay, no free lunch. If you're using CRCs, please look up a standardized or pick one that has that is a primitive polynomial which can guarantee the error detecting capability of a CRC, right? Okay. So let's look up a simple CRC calculation, right? So the first goal is, so I'm going to pick this simple generator polynomial here, which is 1101. So if you like, this is degree 3, and so because this is x to the power 0, x to the power 1, x to the power 2, and x to the power 3. So in other words, it's like 1 plus 0, 1, 2, 3, right? Something like that, okay? So if you wanted to make, so this is degree 3, so that means we end up with 3 bits remainder, or in other words, R is equal to 3. We're guaranteed to be able to correct burst length of up to 3 bits, okay? So here's the data bit we're going to send. So remember, to be able to find the remainder, the process is really simple, right? We got to, what we do is we bit shift by R bits, because it's stuff you want to add R bits to the bit string. So I've got these squares to make me not go wrong on this. So I have 1, 0, 0, 1, 1, 0, 1, 0. So if I bit shift by R, so 1, 2, 3, okay, so that was my multiplying by 2 to the power R, right guys? And then I'm going to do something that you guys did in high school, maybe you've forgotten, right? Polynomial division, who remembers? No, nobody? No offense? Okay. So I'm going to divide by 1101, 1101, okay? So you take the highest degree here is 1, 1, so there's one of them here, and then you multiply out, so it's 1, 1, 0, 1, right? And then you subtract to find what remains. So remember, subtraction and addition is just what? What did I say? XOR, right? Everything is XOR, okay? Right? They're the same, right? Because we don't care about carry, everything is an XOR operation, right? So that means, so 1, 1, 0, 1, 1. Hope you guys remember how XOR works, exclusive OR, right? This is a 0, right? And then clearly this degree is smaller than that, so I need to bring one more, right, from here, because this is only 3 bits, but divisor here is 4, so I bring the 1 up from there. And now I can try to divide this number, okay? So there's these two match, that's a 1. So let's subtract 1, 1, 0, 1. And remember, subtract is just XOR, right? Because I told you everything is modulo 2 arithmetic, right? With no carry, okay? No carry, nothing, everything is XOR, right? So this is a, so take XOR, obviously this is a 0, 1, 0, 1, 1 is a 0. Bring this down. Now I can divide, because clearly it's too small, and I have a 1, multiply out, 1, 1, 0, 1, then again XOR, right? So that's a 1 XOR 1 is 0, so what's a 1, 0, 1? Bring this one down. So I end up with, again, it's the same operation as before. I'll put that up there, and end up with 1, 1, 0, right? Not enough, it's too small. Bring this down, 1, 1, 0, 1. Stop me before I make a mistake. I don't want to do it again. So 1 up there, multiply out. Oh wait, I did that already. See? So take exclusive ORs to just write XOR here. Can you guys see? Yes. So 1 XOR 1 is just a 0, so that's a 0, and that is a 0, and this is a 1, right? And can't divide. So I get the 0, can't divide, right? Bring another one. So finally you can divide. Nope, still can't. Bring the other one down. Yep, finally can divide. So multiply it out. So it's 1, 1, 0, 1, and end up with 1, 0, 1. From memory, I think that's the right answer. Okay. So this is now your R, or the CRC. Which goes here. Okay? So if everything is, so what we send back to the sender, so the sender that's using this generator polynomial would then typically send the data, right, and your R, okay? So in this case it will be 1, 0, 0, 1, 1, 0, 1, 0, and your R is a 1, 0, 1. Right. So this is your remainder. Now, this may go down the noisy channel. and you have a receiver. So what do you guys